Hi students, in this session we are going to discuss about how to find the Fourier transform of cosine wave and Fourier transform of sine wave. After that I will discuss about the properties of Fourier transform. Fourier transform properties. Okay, first I will start with a cosine wave. So how to find the Fourier transform of cosine wave. Okay. So first I will start with cosine wave. So the cosine wave is represented with cos omega naught t. Cos omega naught t. So I have to find the Fourier transform of this cos omega naught t. Okay. So how to find this? First here they are given x of t equal to cos omega naught t. We have to find out the Fourier transform, that is x of omega is nothing but Fourier transform of x of t. Fourier transform of x of t. So simply we can write x of omega as Fourier transform of x of t. Okay, Fourier transform of x of t, that will be equal to Fourier transform of cos omega naught t. Fourier transform of cos omega naught t. Okay. Now, to find the Fourier transform, I will convert this of cos omega naught t into complex exponentials. Complex exponentials. So we have the formula. What is the formula for e power j theta plus e power minus j theta by 2? So e power j theta plus e power minus j theta by 2 is nothing but cos theta. Cos theta. Simply, how can you get this? So here e power j theta means cos theta plus j sin theta plus e power minus j theta is cos theta minus j sin theta. Cos theta minus j sin theta and whole divided by 2. So j sin plus j sin theta minus j sin theta gets cancelled. Cos theta plus cos theta, so that will be equal to 2 cos theta by 2. 2 gets cancelled, that will be equal to cos theta. Okay, cos theta. So the formula for cos theta is this one, e power j theta plus e power minus j theta by 2. Using that one, what will be the formula for cos omega naught t? That means in place of theta I am writing omega naught t. So formula will be equal to e power j omega naught t, e power j omega naught t plus e power minus j omega naught t divided by 2. So in place of cos omega naught t I can write e power j omega naught t plus e power minus j omega naught t by 2. Both are same by using this explanation. So here in place of this one, what I can write? This one, that is, this will be equal to Fourier transform of cos omega naught t, e power j omega naught t plus e power minus j omega naught t divided by 2. You can write like this. Okay. So nothing but finally I get this as Fourier transform of 1 by 2 into e power j omega naught t plus e power minus j omega naught t. Right, like this. So here also I can take 1 by 2 as outside of this one because it is a constant. It is a constant, or simply you can write that as 1 by 2 outside. Fourier transform of e power j omega naught t plus e power minus j omega naught t. Okay, and we can separate this also. So finally, how can you write? So 1 by 2 into Fourier transform of e power j omega naught t plus Fourier transform of e power minus j omega naught t. Simple. So why we convert it like this? Because we already know the formula of Fourier transform for e power j omega t. That is a complex exponential function. So I already explained you how to find the Fourier transform of this complex exponential function. So there is no need to do again everything. So I can use that formula. So what is the Fourier transform of this complex exponential function? What is the Fourier transform of e power j omega naught t? Well known. The Fourier transform of e power j omega naught t is 2 pi into del of omega minus omega naught. So I can use that one directly. So that will be equal to 1 by 2 into, so this one. The formula for this one is, this one I can write 2 pi into del of omega minus omega naught plus, so the Fourier transform of e power j omega naught t, the Fourier transform of e power j omega naught t is 2 pi into del of omega minus omega naught. So the Fourier transform of e power minus j omega naught t is 2 pi into del of omega plus omega naught. The only change is here it is plus, hence we got del of omega minus omega naught. Here it is minus, we get del of omega plus omega naught. So simply you can write the formula as 2 pi into del of omega plus omega naught So simply that will be equal to, here I can take 2 pi as common. Okay, I can bring that as outside this one. Okay, because both 2 pi. Okay, so 1 by 2 into 2 pi into del of omega minus omega naught plus del of omega plus omega naught. Okay, so 2 gets cancelled. So that will be equal to, so here pi of del of omega minus omega naught plus del of omega plus omega naught, a plus b. So you can write this first one, that is b plus a, both are same. So I will write this as first one, that is pi into del of, I am writing this one, del of omega plus omega naught plus del of omega minus omega naught. Okay, so this is nothing but our Fourier transform of the given sine wave. Okay, so the Fourier transform of the sine wave is nothing but pi into del of omega plus omega naught plus del of omega minus omega naught. So with this we can find the, by this way we can find the Fourier transform of cosine wave. Okay, simple. So how the cosine wave will look like? A cosine wave will be like this. This is cosine wave. T x of t. Okay, that is cos omega naught t. So for this, if you want to write the magnitude spectrum and amplitude spectrum, so mode of this one. So this is all real parts. There is no imaginary part. We have only a real part. So we have the magnitude spectrum, and the phase spectrum is also 0 for all the values. So for the magnitude spectrum, how can you get? We get the impulses. I will explain. So we know the Fourier transform of cos of omega t is equal to pi into del of omega plus omega naught plus del of omega minus omega naught. So I explained how to get the Fourier transform of cos omega naught t. Okay, from that derivation I concluded that Fourier transform of cos of omega naught t will be equal to pi into del of omega plus omega naught plus del of omega minus omega naught, or we can represent it another way as this cos omega naught will have a Fourier transform, pi into del of omega plus omega naught plus del of omega minus omega naught. So we can represent like this. So we can represent like this, or we can represent like this. Okay, so these are the two representations for representing the Fourier transform pair. So this is the Fourier transform pair, or the Fourier transform of the signal will be equal to this one. Okay. Now we will go for finding the magnitude spectrum and phase spectrum of this one. See, this will be the magnitude spectrum and this will be the phase spectrum. So how we get this? Simply, first of all, we have to find the mode of x of omega, because this is nothing but our x of omega. Okay, see here, x of omega will be equal to pi into del of omega plus omega naught plus del of omega minus omega naught. So this is our x of omega. So from that x of omega, I have to find out the magnitude of x of omega. So this is x of omega. So from that I have to find magnitude. So magnitude is a square root of real part square plus imaginary part square. So here we have only real parts. Real parts. So this will be the magnitude, because we have only the real parts. So square root of real part square. Square root square cancel. So I will get magnitude also. Okay. So for that value, I have to plot the graph with respect to omega. That is the plot of omega versus magnitude of x of omega will give the magnitude spectrum. Okay, so here I have to take the omega values. See, this function is having a value of 1, only the value inside the bracket is 0. When will it will be 0? Whenever omega value will be equal to minus omega naught. Omega value will be equal to minus omega naught, then minus omega naught plus omega naught. 0, del of 0, 1. Del of 0, 1. 1 into pi. At the same time, as this is minus omega naught, here if you put minus omega naught, minus 2 omega naught, del of minus 2 omega naught is 0, because this del function is having a value of 1, only the value inside the bracket is 0. Whenever this is 0, then it has 1. Otherwise, the value of the function is 0. So here, other than minus omega naught, if you place anything, the value will be 0. In the same way, I want to get this value. Here I have to substitute the value of omega naught in place of omega. So I place omega naught. Then what happens? Omega naught minus omega naught, 0. Del of 0, 1. Okay. So this function will have values 1 at omega equal to minus omega naught, other at omega equal to plus omega naught. Only these two values. So first I will take omega equal to minus omega naught. So at this point, so in omega I consider minus omega naught. So substituting minus omega naught in two places. So this become minus omega naught plus omega naught, 0, and minus omega naught minus 2 omega naught. So del of 0 is 1, del of minus 2 omega naught is 0. So 1 plus 0, 1 into pi. So we have a value of pi. Clear? So at minus omega naught. In the second case, omega naught. So substitute omega naught. That is omega naught plus omega naught, 2 omega naught. So del of 2 omega naught, 0. Del of 0 is 1. Del of anything except 0 is 0. So del of 2 omega naught is 0. Here, omega naught minus omega naught, 0. Del of 0 equal to 1. 0 plus 1, 1 into pi. So at omega naught, the value is pi. Okay, so at minus omega naught it is pi, and at omega naught also it is pi. For all the remaining values, we don't get 0 here, we don't get 0 here. That is, both are 0. 0 into anything is 0. For all the remaining values, it is 0. So this is nothing but the magnitude spectra. Okay, so the magnitude spectra is only at 2 points. That is at omega naught and minus omega naught. At omega naught, we have this value as 1. At minus omega naught, we have this value as 1. So at omega naught, 1 into pi, or minus omega naught, 1 into pi. Clear? So this is the magnitude spectrum. Here there is no imaginary term. So angle of x of omega, phase of x of omega, tan inverse of imaginary part by real part. Imaginary part is 0. 0 by anything is 0. Tan inverse of 0, that is 0. There is no phase angle. Hence there is no graphs. If you want to get as 2 points, so the 2 points are at omega equal to omega naught and at omega equal to minus omega naught, the value is 0. Hence I plotted the graph like this. This is nothing but the phase spectrum. So this is regarding magnitude spectrum and phase spectrum, and this is the representation of our signal cosine wave. So how we will represent the cosine wave? So the cosine wave starts from here. So this is the representation of cosine wave. So here first I explained you how to find the Fourier transform of an cosine wave. Okay, I just converted the cosine wave into complex exponential. So using the formula, already I know the Fourier transform of a complex exponential function. Using that formula, is that Fourier transform of complex exponential function. I got the Fourier transform of cos omega naught t as this one. Okay. After that, I have to go for the finding the magnitude spectrum and phase spectrum. For that, first I represented the given cosine functions. So this is the equation format, this is the diagrammatic format. So the cosine function will be like this. The cosine function will be like this is the cosine wave. So for this, I have to draw the magnitude spectrum. So magnitude spectrum is nothing but the plot of frequency versus magnitude of x of omega. So I know the value of x of omega. In that, I need the mod of x. I find the mod of x of omega because that is having only real part. That will be nothing but mod of omega. So here, this using this equation, I can get the graph only in two parts. That is, the value of this will be 1 only at omega equal to omega naught and omega equal to minus omega naught. In all the other cases, it is 0. So I got the magnitude spectrum at only two parts. And there is no imaginary part, so the phase angle will be equal to 0. That is, at omega naught it is 0 and at minus omega naught also it is 0. So this is like phase spectrum. So this is completely about the cosine wave, the Fourier transform and magnitude spectrum and phase spectrum. Next, we move on to the sine wave. Next one is sine wave. So here we have to find out the Fourier transform of a sine wave. Generally, the sine wave is represented with sine omega naught t. Sine omega naught t. So for this, we have to find out the Fourier transform. Okay, the given function x of t is sine omega naught t. For this, we have to find out the Fourier transform. That is x of omega, which is nothing but Fourier transform of x of t. So here we will find the Fourier transform. The same procedure, we will use the same procedure what we used for a cosine wave. There I converted the cosine function into complex exponentials. So here also I have to convert this sine function into complex exponentials using the formula. You all know the formula for that one. That is e power j theta minus e power minus j theta by 2j equal to sine theta. Sine, simple. So cos theta plus j sin theta minus of cos theta minus j sin theta. So what happens? Cos theta because plus into minus and minus of minus plus. So cos theta gets cancelled, and here we have j sin theta, and here also minus of minus plus j sin theta. That is 2j sin theta. 2j gets cancelled and sin theta. So using this formula, first I have to convert this sin omega naught t. So how can I write the sin omega naught t? So using this formula, what is the value of sin omega naught t? Sin omega naught t equal to sin omega naught t equal to. So in place of theta, I had taken omega naught t. So the formula becomes e power j omega naught t minus e power minus j omega naught t by 2j. So this is the formula. So this sin omega naught t can be represented as this one. Can be represented as e power j omega naught t minus e power minus j omega naught t by 2j. So f of x of omega equal to f Fourier transform of x of t. That will be equal to Fourier transform of sine omega naught t. That is nothing but Fourier transform of sine omega naught t is e power j omega naught t minus e power minus j omega naught t by 2j by 2j. So I can take 2j outside of this one. So if we take a 2j outside of this one, how can I write? Oh, I am directly writing this one. 1 by 2j into Fourier transform of e power j omega naught t and I am separating this one. So I am taking outside of this one and I am separating this one also. That is minus Fourier transform of e power minus j omega naught t. Okay, that will be equal to 1 by 2j. You all know the Fourier transform of these complex exponential functions. The complex exponential function having the Fourier transform 2 pi into del of omega minus omega naught. So in this place I can substitute that value, that is del of 2 pi into del of omega minus omega naught. So we know the formula of complex exponential function, that is the Fourier transform of complex exponential function. The Fourier transform of complex exponential function e power j omega naught t is 2 pi into del of omega minus omega naught. Minus. So, for e power j omega naught t, the Fourier transform is 2 pi into del of omega minus omega naught. For e power minus j omega naught t, the Fourier transform is 2 pi del of omega plus omega naught. Omega plus omega naught. So take 2 pi as common. That is 1 by 2j into 2 pi. Into 2 pi. That is del of omega minus omega naught minus del of omega plus omega naught. Omega plus omega naught. So 2 gets cancelled. So 1 by j can be written as minus j. 1 by j can be written as minus j. That is minus j pi into del of omega minus omega naught minus del of omega plus omega naught. Of omega plus omega naught. So this is the Fourier transform of our sine wave. Fourier transform of our sine wave. So finally, how can you write? So x of omega equal to minus j pi. So omega equal to minus j pi into del of omega minus omega naught minus del of omega plus omega naught. So this one, or simply you can write like this: Fourier transform. So no need to write ft of. You can directly write f of. Okay, you can write Fourier transform of given function sine omega naught t will be equal to minus j pi into del of omega minus omega naught minus del of omega plus omega naught. Omega plus omega naught. Okay, or you can represent this Fourier transform pair as sine omega naught t will have a Fourier transform as minus j pi into del of omega minus omega naught minus del of omega plus omega naught. Omega plus omega naught. So you can represent like this or like this. So you can denote the Fourier transform like this, or you can represent the Fourier transform like this, the Fourier transform pair. So this is the way to find the Fourier transform of sine wave. So for this, if you want to find the magnitude spectrum and phase spectrum, so I'm giving that for your work. So you have to draw the magnitude spectrum and phase spectrum for this sine wave. Okay, that is for your practice. Okay, now we move on to the properties of a Fourier transform. Now we will discuss about the properties of Fourier transform. Here I had given you 12 properties of Fourier transform. They are: the first one, linearity property; second one, time shifting property; third one, frequency shifting property; a fourth one, time reversal property; and the fifth one, time scaling property; sixth one, differentiation in time domain property; and seventh one, differentiation in frequency domain property; and eighth one, time integration property; and ninth one, convolution property; and the 10th one, multiplication property; 11th, duality or symmetry property; and 12th, the last one is conjugate property. So I had given 12 properties. Okay, see, in Fourier series also you have the properties, that is the properties of Fourier series. There also you have linearity property, time shifting property, frequency shifting, time reversals, time scaling, everything. There also we have all these properties. While going for the proofs of the properties, we had taken the formulas of Fourier series. Here we are going for the properties of Fourier transform. So here, while going for the proofs of this, we will take the formulas of Fourier transforms. That is the difference. So while proofs, there we will use Fourier series formulas. Here we will use Fourier transform formulas. So there is an analogy between the properties of Fourier series and properties of Fourier transform. So if you are able to remember those properties, it is easy to remember these properties. So there is a similarity. Okay. For that reason, I explained each and every property there. So here also first I will explain the properties one by one. Okay, after that I will go for the proofs. So first I will start with linearity property. Linearity property. So here in this linearity property I need two signals. Why? Because here in linearity property I have to go for weighted sum of the two signals. Weighted sum of the two signals. Whenever there is a summation or addition, we need two signals. Two signals. So for that reason I have taken the two signals as x1 of t and x2 of t. x1 of t and x2 of t. So x1 of t is having a Fourier transform capital X1 of omega. Here the small x1 of t is having a Fourier transform capital X1 of omega, and small x2 of t is having a Fourier transform capital X2 of omega. Okay, while I am reading, I won't read small x1 of t and capital X1 of t. I will just read x1 of t and x1 of omega like that. Okay, just it is the first one. I read like small x1 of t, because in time domain we will use the small letters and in the frequency domain we will use the capital letters. Okay, so for the signal input signal x1 of t, the Fourier transform I taken as x1 of omega, and the signal x2 of t, the Fourier transform is x2 of omega. x2 of omega. Then the linearity property states that a into x1 of t, a into x1 of t plus b into x2 of t will have a Fourier transform a into x1 of omega plus b into x2 of omega. A into x1 of omega plus b into x2 of omega. That is, here the weighted sum of the two input signals is equal to the weighted sum of their individual Fourier transforms. The weighted sum of the two signals is equal to the weighted sum of their individual Fourier transforms. Individual Fourier transform, because for x1 of t the Fourier transform is x1 of omega, for x2 of t the Fourier transform is x2 of omega. That means here the weighted sum, that is x1 of t is multiplied with a and x2 of t is multiplied with b. So a into x1 of t plus b into x2 of t is nothing but the weighted sum of two signals, that is equal to the weighted sum of their individual Fourier transform. That is, x1 of omega is multiplied with a and x2 of omega is multiplied with b. Okay, so simply we can say here the linearity property states that the weighted sum of the two signals is equal to the weighted sum of their individual Fourier transform. Or simply, if x1 of t is having a Fourier transform x1 of omega and x2 of t is having a Fourier transform of x2 of omega, then a into x1 of t plus b into x2 of t is having a Fourier transform a into x1 of omega plus b into x2 of omega. Okay, so I said while I going for the time domain I will use the small letters, while I going for the frequency domain I will use the capital letters. Okay, whenever there is a change then I will say that is small and capital whenever there is a change, otherwise I won't say small and capital. Okay, now the second one is time shifting property. Time shifting property. So there is a shift in the time domain. There is a shift in the time domain. So if the signal x of t is having a Fourier transform x of omega, so here the shifting is done in time domain, hence we need one signal is sufficient. The signal is x of t is sufficient. So here there is no need of two signals. For that reason I am taking only one signal. That is, that signal is shifted in time domain. Signal started here, it may start either here or there. Okay, that signal is shifted. Okay, for that reason I have taken only one signal, and that has x of t. If x of t is having Fourier transform x of omega, then time shifting means x of t minus t naught. X of t minus t naught will have a Fourier transform e to the power of minus j omega t naught into x of omega. T naught into x of omega. That is, whenever there is a shift in the time domain, in frequency domain the x of omega should be multiplied with e power minus j omega t naught. This x of omega should be multiplied with e power minus j omega t naught. That is, whatever the shift is here t naught, that will resemble there. That is, this t naught will comes here. That is, if we take this as m, here we will get m. Whatever the change is here, the change will occur here. Okay, so time shifting property states that if x of t is having a Fourier transform x of omega, then x of t minus t naught will have a Fourier transform e power minus j omega t naught into x of omega. Next we go for frequency shifting property. Frequency shifting property, that is, if For frequency shifting property also I need only one signal. Hence I have taken x of t, and x of t is having a Fourier transform x of omega. Then e power j omega naught t into x of t. E power j omega naught t into x of t will have a Fourier transform of x of omega minus omega naught. The property is frequency shifting property. That is, frequency should shift. So frequency is x of omega. X of omega should shift. That is x of omega minus omega naught. For that frequency to be shifted, here the signal x of t should be multiplied with e power j omega naught t. See, here it is shifted with omega naught. So x of omega has changed to x of omega minus omega naught. So that omega naught comes here. So whatever we have taken here, that will comes here. So here in frequency shifting property, the signal x of t is multiplied with e power j omega naught t. Then we will have the Fourier transform of x of omega minus omega naught. Whatever the shift is there, it will comes same as both ends. That is, here if you take omega naught, there also it comes omega naught. If you change the variable, there also the variable changes. Simple. If x of t is having a Fourier transform of x of omega, then e power j omega naught t into x of t will have a Fourier transform capital X of omega minus omega naught. Okay, this is regarding frequency shifting property. Okay, next I will go for time reversal property. Time reversal, that is x of t will changes to x of minus t. Time reversal. For this also I need only one signal. So if x of t is having a Fourier transform x of omega, then the time reversal property states that x of minus t will have a Fourier transform capital X of minus omega, capital X of minus omega, capital X of minus omega. Clear? So simple, time reversal, x of t changes to x of minus t and x of omega changes to x of minus omega. Next, time scaling property. Time scaling. So here I have to multiply the variable t with a constant. That means the signal should either be compressed or expanded. The given signal should be compressed or expanded based on the constant that is multiplied with the variable t. So here I have to multiply the variable t with a constant. So based on that constant, the signal either be compressed or expanded. That is, only one signal is sufficient. Hence I have taken the single signal x of t. If x of t is having a Fourier transform x of omega, then time scaling property states that x of at, that is, here the variable t is multiplied with the constant a. I taken the constant as a. X of at, that means based on this a, I will have either a compression or expansion of the signal. Okay. Then the time scaling property states that x of at will have a Fourier transform 1 by mod a into x of omega by a. 1 by mod a into x of omega by a. Okay, simple. Here I am multiplying with a constant. So the change will have to occur at this end, like 1 by mod a into capital X of omega by a. Simply, if x of t is having a Fourier transform x of omega, then x of at will have a Fourier transform 1 by mod a into capital X of omega by a. This is time scaling property. Now go for the differentiation property. So here we have differentiation in time domain as well as we have the differentiation in frequency domain. So I will go for both. First I will explain with differentiation in time domain property. So differentiation in time domain. If x of t is having a Fourier transform x of omega, I am considering only one signal because I can perform the differentiation of a single signal itself. Hence I have taken only one signal. So if x of t is having a Fourier transform x of omega, then the differentiation in time domain property states that d by dt of x of t, that means we have to go for the differentiation of the given signal. D by dt of x of t will have a Fourier transform j omega into x of omega, that means here the x of omega is multiplied with j omega. Okay, whenever we go for the differentiation of the given signal in its Fourier transform, the x of omega will be multiplied with j omega. Simple. So if x of t is having a Fourier transform x of omega, then d by dt of x of t, that is the time differentiation in time domain, d by dt of x of t will have a Fourier transform j omega into x of omega. So this is differentiation in time domain. Now go for the differentiation in frequency domain. So for that also we need only one signal. Hence I have taken, if x of t is having a Fourier transform x of omega, then Then, so we have to go for the differentiation in frequency domain. We have to go for the frequency domain. That means I am multiplying the given signal with a t. Here I am multiplying the given signal with a t. Hence I am writing that the differentiation in frequency domain property states that t into x of t, t into x of t will have a Fourier transform j into d by d omega into x of omega. Simply differentiation of x of omega with respect to omega, j into d by d omega of x of omega. Okay, so differentiation in frequency property states that if x of t is having a Fourier transform x of omega, then the differentiation in frequency domain states that t into x of t, t into x of t will have a Fourier transform j into d by d omega of x of omega, j into d by d omega of x of omega. See, here the differentiation takes place in time domain, and here the differentiation takes place in frequency domain. Hence it is nothing but differentiation in time domain, and it is differentiation in frequency domain. Because the difference, if the differentiation takes place in time domain, then we call it as differentiation in time domain property. If the differentiation takes place in frequency domain, then it is differentiation in frequency domain property. Okay, so in differentiation in time domain, the x of omega is multiplied with j omega, and x of t is differentiated with respect to t. In differentiation in frequency domain, x of t is multiplied with t, and x of omega is differentiated with respect to omega. So this is recording differentiation in time domain and differentiation in frequency domain properties. Next I go for the time integration property. Integration property is simple. Actually here I got the j omega as a multiplication of this one. So here I will get the j omega as division of this one, because there is a relation between integration and differentiation. So for differentiation, if I got j omega as the multiplication of x of omega, in integration I will get j omega as division of x of omega. Simple logic. In differentiation I got j omega as multiplication of x of omega. In integration I got j omega as a division of x of omega. Okay, so see, in time integration property I can perform the integration on a single signal. Hence I have taken only one signal. If x of t is having a Fourier transform x of omega, then simply you can write integral x of t dt will have a Fourier transform 1 by j omega into x of omega. You can write simply, or if you want to write exactly, then you have to apply the limits. So if you are able to remember these limits, write it exactly. If you are not able to remember the limits, you can write like this. If x of t is having a Fourier transform x of omega, then the time integration property states that integral x of t dt will have a Fourier transform 1 by j omega into x of omega. Simply write like this. If you are not able to remember the limits, if you want to write it exactly, if you want to write it exactly, write like this. That is, if x of t is having a Fourier transform x of omega, then integral minus infinity to t x of tau d tau, x of tau d tau will have a Fourier transform 1 by j omega into x of omega if x of 0 equal to 0. This is an important condition. So here we have to consider x of 0 equal to 0, then only this will be possible. If x of 0 is not equal to 0, then the property will change. So we have to mention or specify this one. Okay, I will explain everything while I will go for the proofs. Okay, now I am going for the outlines of all these properties. Now I am explaining the outlines of all these properties. Okay, in these properties I will explain the proofs for some properties, and you have to do the remaining properties as your work. Okay, so in time integration property, if x of t is having a Fourier transform x of omega, then integral minus infinity to t x of tau d tau will have a Fourier transform 1 by j omega x of omega if x of 0 equal to 0. Simple. This is x of tau d tau. After integration I have to apply the limits. Limits is in t, so the equation will comes in t. So if you are not able to remember this, simply you will write integral x of t dt. Integral x of t dt. That will have a Fourier transform 1 by j omega x of omega. Or if you want to write it perfectly, write this integral minus infinity to t x of tau d tau having a Fourier transform 1 by j omega x of omega if x of 0 equal to 0. So finally, if x of t is having a Fourier transform x of omega, then time integration property states that integral minus infinity to t x of tau d tau will have a Fourier transform 1 by j omega into x of omega if x of 0 equal to 0. This is recording time integration property. Now go on to the convolution property. This convolution and multiplication both have a relation. Here, differentiation and integration have a relation. That is, j omega is multiplied in one thing and the j omega is divided in another one. There is a relation. In the same way, this convolution and multiplication will also have a relation. So we will see that relation. First, I will explain you the convolution property. So for addition, subtraction, we need two signals. For multiplication also, we need two signals. As multiplication and convolution have a link, this convolution also needs two signals. So for that reason, I have taken x1 of t is having a Fourier transform x1 of omega, and x2 of t will have a Fourier transform x2 of omega. I had taken two signals, and for the two signals, the first one x1 of t and the second one x2 of t. The first one x1 of t is having Fourier transform x1 of omega, and the second one x2 of t is having a Fourier transform x2 of omega. Then the convolution property states that x1 of t convolution x2 of t. Here the convolution is represented with the star mark. Okay, addition with a plus, multiplication with into. In the same way, the convolution will be represented with a star mark. Then the convolution property states that x1 of t convolution x2 of t will have a Fourier transform x1 of omega into x2 of omega. x1 of omega into x2 of omega. Simply here, the convolution of the signals in the time domain is equal to the multiplication of the signals in the frequency domain. So in the time domain it is convolution, in the frequency domain it will become as multiplication. That means their spectrums will be multiplied. The two signals are convoluted in the time domain, then their spectrums will be multiplied. Simple. Time domain, if it is convolution, in frequency domain it is multiplication. So based on this, I can go for the multiplication property also. So there is a reverse of this one. Okay, first clearly know the convolution property. In convolution property, if x1 of t is having a Fourier transform x1 of omega and x2 of t is having a Fourier transform x2 of omega, then x1 of t convolution x2 of t will have a Fourier transform x1 of omega into x2 of omega. Now come to the multiplication property. So for multiplication also we need two signals, that is x1 of t and x2 of t. So x1 of t is having a Fourier transform x1 of omega and x2 of t is having a Fourier transform x2 of omega. Here the multiplication property states that x1 of t into x2 of t, that is, there is a multiplication in time domain. What happens? In frequency domain, we go for the convolution. As there is a multiplication in time domain, we have the convolution in frequency domain. Hence, x1 of t into x2 of t having a Fourier transform 1 by 2 pi into x1 of omega convolution x2 of omega. So here we have the convolution. So while going for the proofs, we will get 1 by 2 pi. Hence they had 1 by 2 pi into x1 of omega convolution x2 of omega. So these two has a link. Simple. So in multiplication property, the multiplication in the time domain will be converted into convolution in the frequency domain. Hence I say x1 of t is having a Fourier transform x1 of omega and x2 of t is having a Fourier transform x2 of omega. Then x1 of t into x2 of t into x2 of t will have a Fourier transform 1 by 2 pi into x1 of omega star x2 of omega. That is x1 of 1 by 2 pi into x1 of omega convolution x2 of omega. Okay. Now, so here in convolution property, in time domain we have the convolution, and in the frequency domain we have the multiplication. In multiplication property, in time domain we have the convolution, and in the frequency domain we have the convolution. In multiplication property, in time domain we have the multiplication, and in frequency domain we have the convolution. And the duality property, next one is duality property. So duality property is also called as symmetry property. So for this I need only one signal. Hence I have taken x of t is having a Fourier transform x of omega. X of t is having a Fourier transform x of omega. Then see here capital X of t. So this is small x of t. This is capital X of t because we are going for duality or symmetry. Hence I written capital X of t will have a Fourier transform 2 pi into small x of omega, small x of minus omega, small x of minus omega. Remember, up to now I represented t with respect to small x and I represented omega with respect to capital X. But in this duality property, the changes this one, the small x will be converted to capital X and the capital X has been changed to small x. Remember this is very, very important. If x of t is having a Fourier transform capital X of omega, then capital X of t will have a Fourier transform 2 pi x small x of minus omega. So the changes occurs here. Okay, the changes occurs. So we have to remember this one. So we have to write in duality property, if small x of t is having a Fourier transform capital X of omega, then the duality property states that small x of t will have a Fourier transform 2 pi into small x of minus omega. So remember these two, okay. So if small x of t is having a Fourier transform capital X of omega, then capital X of t will have a Fourier transform 2 pi into small x of minus omega. 2 pi into small x of minus omega. This is nothing but duality property or symmetry property. And the last one is conjugation property, simply conjugate property. What is conjugation property? For this conjugation property also we need only one signal, hence I have taken one signal as x of t. If x of t is having a Fourier transform capital X of omega, if small x of t is having a Fourier transform of capital X of omega, then conjugate x star of t, then conjugate of this x of t, this x star of t will have a Fourier transform capital X star of minus omega, simple. Here I have to go for the conjugate. If you go for the conjugate, then its Fourier transform will have a conjugate of a reversal, that is x star of minus omega, So the conjugate property, in conjugate property, if x of t is having a Fourier transform x of omega, then x star of t will have a Fourier transform x star of minus omega, okay. So if you want to read it perfectly, if small x of t will have a Fourier transform capital X of omega, then small x star of t will have a Fourier transform capital X star of minus omega. So I already told you. So while reading, I will read directly as x of t and x of omega. With respect to t, it is small x, and with respect to omega, it is capital X. Clear? This is the explanation about all the 12 properties of this Fourier transform. So I explained all the 12 properties of this Fourier transform. Now we have to go for the proofs. The proofs are very, very important. Okay. So total we have 12 properties. In these 12 properties, I will go for the proofs of either 5 or 6 properties. So the remaining 5 or 6 you have to do at your work. You have to do at your home. So that is for your work. So I will go for the proofs of these some properties. I will go for the proofs of some of the properties in the next class. Okay. And you have to do the proofs of remaining properties at your home, that is for your work. With this I am finishing today's class. Okay, thank you one and all.